This is section 2.3, using the product and quotient rule to find derivatives. Now, first up is the product rule. So whenever you want to multiply two separate functions and find the derivative to that, it's not as easy as just multiplying each individual derivative. You have to follow this rule, which says keep the first function the same. You multiply that by the derivative of the second function. Then you add the second function and multiply it by the derivative of the first function. And we'll work through two examples using the product rule. First example says to differentiate this expression. Now, what I mean by the first and second function, I kind of can think of this as the f function and this over here as the g function. Because then when I go to find my derivative, I can just kind of use the pattern, use the rule of the product rule. So the derivative with respect to x, so dy dx is going to equal, rule says keep f the same, so I'm just going to write this as x to the third plus 1. Now this is going to turn into a g prime, so the derivative of this is going to be negative 8x plus, the rule now says keep g the same, so 2 minus 4x squared. And now I have to multiply that by f prime, for the derivative of x to the third plus 1 is going to be 3x squared. Alright. Next I have to simplify this. So what this means is I have to distribute this negative 8x into here. So it's going to be negative 8x to the fourth minus 8x. Distribute this 3x squared into here. It's going to be plus 6x to the second. And this is going to be minus 12x to the fourth. And then the last thing is to combine like terms. I have like terms on these two. So it's going to be negative 20x to the fourth plus 6x squared minus 8x. And that's your derivative. So dy dx is equal to that. Alright, next example. This time I have the cube root of x multiplied by e to the x. I want to find the derivative to that. And before I begin, I'm going to just write this as x to the 1/3, so I know what exponent to use. I'm still going to be able to use the power rule for this derivative. Alright, so this is just the rewrite portion. And then this is going to be now, again, consider this to be the f portion, and consider this to be a g. And now I can say that g prime is going to equal, following the product rule, keep x the same, or x to the third the same, so it's going to be x to the 1/3. The derivative of e is itself e to the x plus g stays the same, so e to the x. And the derivative now of this, using the power rule, is going to be 1/3. Subtract the power by 1, so it's going to be minus 2 over 3. And now I can go ahead and simplify this a bit. This is going to be the cube root of x times e to the x plus, this is going to be a fraction. It's going to be 3 in the denominator. It's going to be the cube root of x squared, and the e is going to be on top, so it's going to be e to the x plus all of this, and this is what your derivative is. Alright, so those are two examples with the product rule. Now the quotient rule is a little bit more complex. So this is the derivative now for quotients. So what this says is you keep the bottom the same, so you keep g of x the same. You multiply that by f prime minus f of x times g prime all over g of x squared. And there's one little condition, and that's going to be that g of x does not equal 0. Now there's a little, I guess, mnemonic device that I've or a little moniker that I've developed over the years, that the derivative is going to be down z up c prime minus up c down z prime all over down z squared. If this is up c, that's down z. That's maybe a way you can remember it. Down z up c prime minus up c down z prime all over down z squared. And we'll go over two examples with the quotient rule. So this one is going to be finding the derivative to that. So again, I have my quotient rule here. I can think of the top part as f, the denominator as g. And so my derivative is going to be g prime is going to equal, keep the top the same. I'm sorry, keep the bottom the same, I'm sorry. The derivative of f is going to be just 2 minus f stays the same, so it's going to be 2x plus 5. The derivative now of the denominator is just going to be 3 all over the denominator squared. And in case you're wondering how I got these two derivatives, I can make a little note that if I have the derivative of 2x plus 5, I can use the power rule that says this is the exponent of 1, which would give me 2 times 1x to the 0. So this becomes basically just 1, so it's going to be, the derivative of this is just going to be 2. And the same thing could be done with the denominator. Alright, next thing is I have to simplify my derivative. So if I distribute this 2 into the first part, it's going to be 6x minus 4. Distributing the 2 into this. I have to now distribute the 3, so it's going to be minus, put a little bracket, it's going to be 6x plus 15 all over the denominator squared. Last, I can distribute the negative into the bracket, so it's going to be 6x minus 4 minus 6x minus 15. And lastly, I can combine like terms. Positive 6, negative 6 cancel each other out, and I have negative 4, negative 15, so it's going to be negative 19 all over 3x minus 2 squared, and that's my g prime. Alright, last example, number 4. Find the tangent slope to this curve, to this equation at the point 1 and 1/3. Now, even though it doesn't say directly to find the derivative, to find the tangent slope, I need to find the derivative. So I go ahead and set up my y prime to be, because it's a quotient, I have to use the quotient rule. So I'm going to pull this down so we can just follow the pattern. And I'm going to rewrite this so I can see what exponent this is. This is x to the 1/2. So I can use the power rule on that. This is going to be a 2x plus 1. So this is just equivalent to that, so I can see what exponent it has. And now my derivative is keep the bottom the same, 2x plus 1. The derivative now of the top is going to be the power rule on x to the 1/2, which is 1/2 x to the negative 1/2 minus, I then keep the top the same, so I'm going to keep the square root of x the same, so it's going to be x to the positive 1/2. And then the derivative of the bottom is just going to be 2. and then all over the denominator squared. Now, I could go and try to simplify this. However, since all I'm interested in is the tangent slope, I'm interested in a numerical value. So what I can do at this point, instead of simplifying it, because all I'm going to be doing is plugging this number in, is evaluate it at the point they indicate. Since this is a function of x, I'm just going to plug in the x coordinate, which is 1. So I'm going to plug in 1 into all of this. It's going to give me 2 times 1 plus 1. This is going to be 1/2. Well, this is just going to be the square root of 1. I'm just going to put this as 1 to the negative 1/2. And then minus 1 to the 1/2 times 2. It's all going to be 2 times 1 plus 1 squared. Alright, so kind of simplifying this and cleaning this up, I can say that this is going to be 2 times 1 plus 1, which is going to give me a 3. This is just the square root of 1, which remains 1, times 1/2, so it's going to be 1/2. Minus, this is going to be 1 times 2, which is 2. And it's all going to be over 3 squared. And simplifying this some more, this is going to be 3 over 2 minus, to find a common denominator, I put this as 2 over 1, so it's going to be minus 4 over 2, all over 9, and this is going to be negative 1/2 in the numerator, all over 9, which simplifies to be negative 1 over 18. So kind of, I guess going back to the initial problem, I can say that my tangent slope, I can say that y prime at 1 is equal to negative 1 over 18. And that's the tangent slope.